Hi there, it's Manu from Bremsstrahlung. Today I would like to show you a very simplified explanation of radioactivity, like what actually happens there, what makes it dangerous, how does it work, more or less. I built up some very simple models with grapes mainly, and we have some electrical wire and some screws and some Diabolo bullets from my air rifle. Something like that. I'll show you in detail what I'm talking about. Well, let's start here. These are my building blocks for my model. As you see, I have the darker, like the bluish black grapes as my protons. I've got the white grapes as my neutrons. I've got these little Diablo bullets as my electrons. Then I have some Diablo bullets that I just painted red. These will be my positrons. And we even got some neutrinos. I just took some tiny screws to model these. And down here we have the photons. We've got our X-rays, which are a bit longer, and the gamma rays, which have a shorter frequency and are more powerful, therefore. Also, I built myself a really neat model of potassium-39. This is actually quite accurate, I think. Well, this is like normal potassium, like the most common isotope that occurs in nature. You'll have a lot of that in your plant ash from your oven, or in bath salts, or even in food supplement salts. I choose to take this potassium-39 model because uranium just has so much stuff, and I just was bored to count all the grapes. So there is many different kinds of radioactive decay, which I'll tell you about in a moment. But I think for this model, this is really the simplest, most simple thing. And also something important to know. If you don't know what this here is, you should look it up. The periodic table, like this kind of shows you all the elements that are in a particular series. It's like counted by protons, so the lightest is hydrogen with 1 proton, second lightest helium with 2 protons. Then we go on all the way down, like uranium has 92 protons, and it goes even further, as you see. So let's start with some alpha decay. A good example for alpha decay is thorium-232, which is the most common natural thorium isotope around. You can find a lot of stuff of that on Earth. And it will decay by emitting an alpha particle, and that's basically 2 protons and 2 neutrons strapped together, like these over here. And for this example, the thorium-232 will decay to radium-228. So that's how these atoms kind of change themselves, also through radioactive decay. Well, yeah, this here like gets too heavy, it doesn't like to have so many stuff inside, and it just kicks out this alpha particle, and it will be radium afterwards. That's interesting. So let's head on to beta decay. Beta decay is basically if a radioactive element kicks off electrons. But what happens in detail, it's actually quite interesting. This is a model of a tritium atom. It's the same stuff you have in these glow-in-the-dark keychains. And tritium is radioactive, so what will happen in beta decay of tritium in this example is one of the neutrons will decay. It will turn itself into 1 proton, 1 electron, and 1 neutrino. But the proton doesn't leave the atom, it will actually stay here. And this will turn itself into helium-3. It's like a heavy helium. No, actually it's a light helium. It has a neutron less than normal helium. That's interesting. And also it will kick off a neutrino. That's very fascinating too. So that's beta minus decay, the most common beta decay. So finally we'll come to gamma decay. Gamma radiation will happen when electrons actually move their energy states, which I'll come to in a minute to explain you that. But the big difference here is that a gamma ray is a photon, so it's basically light. It's a light particle wave thingy, whatever it is. Also, X-rays, we have them over here. They are kind of like a weaker kind of gamma rays. There is like a difference, but in general, it's very simplified, but they're also photons, so they're also light. I will put these two in the same category, more or less, just for simplification. So back to our atomic model here for a moment. I actually changed it. I made it radioactive. I just put an extra neutron into the nucleus. So now it's potassium 40. Maybe just some words to atomic models in general. This here is Niels Bohr's model with the fixed electron shells, or like the energy states that they can be on. Like an electron really only can be on one certain orbit here, even though the whole orbiting is really out of date. Like before this model there was Rutherford's model, which was kind of like a solar system, like every electron has like an orbit and stuff. And I think before that there was even like something called the pumpkin plume model or something. Like very awkward things, very interesting. But actually even this here is outdated. I mean, meanwhile there's the quantum model, which says that an electron doesn't have a fixed position inside of an atom. It's more in a wave shape, I guess. Because, you know, I've seen electrons in the cloud chamber. Like, you can see them as particles going a certain path. But here, I like to imagine it like a bit like a force field, like in Star Trek or something. Like, when a phaser hits the ship, then you have this force field around it that protects it, and it's more like an energy field, I would say. It's maybe easier to imagine what this here is. Now it's potassium 40, so it's radioactive. But also what can happen to non-radioactive atoms, or also radioactive ones, is these here can get excited, the electrons. They can move state and kind of like have extra energy then. It can happen if a gamma ray comes flying by, or even if a fast electron comes flying by. Certain atoms are able to emit gamma rays or X-rays out of this excited state just to get their energy balance back to normal. Well, back to our radioactive potassium 40. This will decay by beta minus decay, which I'll explain you in a minute. Okay, quick correction here. We didn't really make it radioactive. Let's just assume we are dealing with a potassium 40 atom in the first place. This, by the way, is the same stuff that makes your bath salt radioactive, or even some food supplement salts. As I mentioned before, this is around everywhere, inside our bodies, in bananas and stuff like that, but it's very little quantity, so it's not that big of a danger, I would say. Well, now it's potassium 40. It's radioactive. It will most likely decay by beta minus decay. So what will happen here is one of these neutrons, let's say this one here, decays. So what will happen is it will kick out a proton, which will stay here. We have a proton more. This changes the atom, and give me a second. Here we have potassium. Now we have calcium. But also from this neutron decay, the neutron will also kick out one of our electron pellets here. And the whole problem with radioactivity, or what makes it dangerous, or velocities, or speed, it's force. That's the whole deal here. I mean, an electron or a helium nuclei, an alpha particle, is not dangerous. It won't do you any harm if you meet it in some back alley at night or something. But the point is, if it's coming towards you in a car or in an airplane at really high speed and it will hit you, that will hurt. And for that, I'll just show you a small example. Well, as I mentioned before, electrons, for example, are not bad for you in general in daily life. You know them, like if you rub a balloon on your hair and they stick up, that's electrostatic charge, that's electrons doing that. Or sometimes they'll maybe shock you a little bit if you get a small electric shock or something, that's electrons too. But these barely move at the speeds that beta electrons do, like the radioactive products, the dangerous things of the radioactivity. So let's say this here is your DNA, it's a part of your cell, and you get electrostatically charged. So let's throw some of these electrons to it. They don't really stick. I thought the double-sided tape will do the job, but it doesn't. So yeah, let's cheat a bit. There, one, another one, and another one. Let's put a fourth one. So we got ourselves some electrons on our DNA, or on our cells, I would say. But let's see now what happens with a beta particle that comes with much higher velocity, with much more power and speed. So here we go, let's give our electrons some velocity, a lot of velocity. Yay, beta decay! That's your DNA over there. Bad for your DNA. So actually at first I thought it didn't really destroy it, but look at this. This is what I mean. That's what happens to your DNA if you get hit by radioactive beta particles, or alpha particles, or gamma rays, or X-rays. That's what makes it dangerous. It's just the energy that's in the stuff. It's not what it is, actually. I want to do a really small experiment just before I end the video about shielding also. You also see a big difference between alpha, beta, gamma radiation if you shield an emitter. So over here I have my small piece of uranium ore. You've seen that in the cloud chamber videos and in others probably. The point is, this is not just pure uranium. The uranium inside also, it decays in time. It will have some radium inside and maybe some thorium and other stuff. So it's not pure. It's not a pure alpha emitter. It does emit a lot of alphas, but it will also emit beta and gamma. So to start with, let's just measure it with the Geiger counter without any shield in between, to see the full value of radiation. Put the sensor about here. And I'll make a quick cut. I'll wait a few minutes till the countings go up to the maximum. Be right back. Okay, I think we're at maximum. So we are around 1540 counts per minute, I would say, with no shielding. So let's write this down. 1540 more or less. So let's see what happens if I put a piece of paper between the Geiger-Miller tube and the uranium ore. Paper is enough to shield alpha radiation, mostly. Most of the alpha particles will be stopped by a piece of paper. Because they're so heavy, they don't really travel that far. They're just not able. They lose their energy really fast, especially in air. I mean, air resistance is a factor, and I think in air they only travel a few centimeters maximum. Then they even get stopped by air. Okay, let's put the shielding in between. Yeah, something like that. I'll do a cut again, and I'll see you when the Geiger counter got its approximate value again. So I think we got us a value again. It's really interesting. It dropped by almost half. I'm around 890, let's say 900 counts per minute, with paper as shielding. 900. And now we will add, or you don't even have to add it, you just could use only this, but I'll just add, I'll only take the aluminium foil for this. This aluminium foil should be able to block most of the beta particles coming out. I don't trust these leptons though, that's why I took it double. Normally they say one sheet would be enough, but I think they are able to penetrate aluminium foil to a certain grade. It's not many that will get through, but some will. But let's just see what happens now. And I'll let it count again, and I'll see you right away. Okay, this is interesting actually. We're not really much below the 900. Actually right now we're even above 900, but that just means that this thing doesn't give off very much beta electrons. Most of the stuff we're still measuring will be gamma, or maybe even X-ray. Maybe there's even some Bremsstrahlung effects, but yeah, now it's even at 920. But just for the sake of the experiment, let's say 850 counts. That's about what I had before, for like a few minutes ago for a while. So this here, I'll just put this here away for the noise. You can do a really simple calculation now. So with no shield, this is alpha, beta and gamma, we have 1540. And with paper, we shielded the alphas, we had 900 counts, and with the aluminium foil, we had, let's say, 850 counts. So actually with these values, we can do a really simple calculation. Well, basically, here the last value is gammas that we counted, gamma radiation, because we shielded off the alphas with paper and the betas with aluminium foil. So we have 850 counts per minute in gamma radiation left. And the difference between this and this is 50, so that means we only have about 50 counts per minute beta radiation. And if you put these together, you get 900 again, and you take these 900 off of the first value without any shielding, then we have 640 counts left, and that will be our alphas. So really simple. This setup was really not scientific and not precise enough, but it's just to show you a simple example, and it actually works quite well. And this is realistic. This is what I expected of my pitch blende sample here. Well, I hope you enjoyed the video so far. Just some last words before I end. I did a small mistake before in explaining beta decay. It's actually not a neutrino, it's an antineutrino that's produced there. But then there's also beta plus decay, which is really interesting. That's where our positrons come in, the red ones. I didn't really talk about these yet. Also potassium 40, our atomic model back here, has a really interesting phenomena. It's in 90% plus minus of all cases, it will just undergo normal beta minus decay. And then there's also like, I think it's about 8% chance that it's something like that's called electron capture happens there, which I didn't really explain now. There's a lot of phenomena I didn't explain. It's complicated and it's a lot of information, and I'll try to put some stuff in the description if you're further interested in these things. But also there is a very small chance that our potassium 40 atom here, I think it's 0.001% of all decays happen in beta plus decay. That actually means that the neutron will decay into a proton, which stays in the nucleus, but it will also decay into a positron, which is the antiparticle to the electron, so it's antimatter. And in a funny way, the antineutrino in beta plus decay is a normal neutrino, it's not an antineutrino. So it makes sense, you know, you get a beta minus electron with an antineutrino, or you get a beta plus positron with a neutrino. So it all makes sense in the end. It is a complicated topic, but I think it's really fascinating just to try to wrap your mind around it, and it's brain training for me somehow. I really enjoy it, and I'll try to put some links if you want further information. There's a lot of great other videos about these topics and this stuff. I hope I can help you out there a bit, and as I said before, I hope you enjoyed. If you did, maybe give me some likes or subscribe or stuff like that. Maybe write me a nice comment. And I don't know what you were doing, but I have a lot of grapes to eat tonight, so see you soon. Bye.